Good afternoon, everyone at home and throughout the country. Thank you for joining today. My name is Tom Stawinski, and I'm the Federal Manager for the Office of Nuclear Energy's Microreactor program. And I've also listed our National Technical Director and also the technical point of contact for this NEOP scope, Dr. Jess Jean out of Idaho National Laboratory. And today I'll be presenting on scope area RC-2, which is related to microreactor cost reduction and end-user application integration. To begin, I'd like to just go through a few slides giving a brief overview of the vision, goals, and objectives of the Office of Nuclear Energy's Microreactor program. So the overall vision of the program is by 2025, the Microreactor program will have supported the advancement of innovative technological breakthroughs for microreactor technologies, will have empowered the initial demonstration of the next advanced reactor in the United States in the form of a microreactor, and then looking ahead, continue their work to enable successful demonstrations of multiple domestic commercial microreactors. Now, to achieve this vision, our program has several primary objectives. And really the overarching objective is to support cross-cutting R&D activities, primarily led through the National Laboratory, but also led through collaborations with both industry and university that really help raise the technical maturity of components and integrated systems for microreactors to allow for their demonstration and subsequent commercial deployment by the early to mid-2020 timeframe. And while doing this, we do remain closely engaged with other stakeholders in microreactors, including the Nuclear Regulatory Commission, industry, universities, and the Department of Defense on related issues and activities to resolve these issues. Now, based on previous stakeholder feedback, we have several specific areas that we've really been working on. The first one is validating integrated microreactor systems and end-user applications in both the non-nuclear and nuclear prototypical environment. And really, the majority of the scope today is really going to focus heavily on that particular area and how universities can help us succeed and advance this area to bring these technologies to fruition. Another important area that is currently being actively supported by universities is maturing cross-cutting technologies, such as heat pipes, advanced moderators, and going on to other advanced heat exchangers and power conversion systems that may be applicable to microreactor technologies. We're also looking at testing and validating unique remote monitoring and semi-autonomous control systems. This is an item that's relatively cross-cutting throughout the nuclear industry, but really has been one of the major selling points of microreactor technologies, is placing them in remote or hard-to-access communities and allowing their operation from remote locations and their monitoring remote locations. So we're really exploring employing tool sets that are being developed throughout the NE programs within our program and seeing how those can best fit specifically to microreactor applications. And we're also looking at near-term and essentially long-term regulatory challenges for microreactor, both demonstrations and commercial entities. Now, we are not looking to identify the issues. That's being done well with other collaborations with industry and within NE programs. We're looking at ways to use our infrastructure and experimental capabilities within the microreactor program to resolve these issues. So I'm just going to briefly go over how our program is set up to really help reach these objectives and perform these activities. And the program is primarily broken into three major areas, and each one in a way feeds into the other. So we begin with systems integration and analysis. And at the past year and a half or so, this has really been focused on looking at cross-cutting challenges and benefits of microreactors, both from a modeling and simulation aspect, both employing NEAMS tool sets, so not developing new tool sets, but really employing them on microreactor design and seeing where those strengths and weaknesses are and how we can help validate some of these code sets and relay information to the NEAMS program and how some of these very innovative, unique tools can be used to help designers optimize their microreactor concepts. Another item that's really been done in this area is performing a variety of techno-economic analyses in microreactors. Really been laying the groundwork of just seeing really what is being looked at from developers and stakeholders, and what are they, what are some of their needs, and how can we relay this information back to microreactor stakeholders and end users to really help them optimize their designs to make their concepts economically viable and meet user needs. And within this area as well, really, as I discussed previously, is looking at some of those unique microreactor regulatory challenges that we may be able to address from a technical sense, from employing and actually utilizing semi-autonomous and autonomous operating regimes to how would one transport one of these reactors to its final site. So these are issues that are being looked at as well. And from this, it really flows into looking more at the development of unique components and building those components in the systems for microreactors. Now, one of the major and promising items for microreactors and heat exchange from the core is heat pipes. While that's not the only technology being considered, we understand that there's still a little legwork that needs to be done to better validate the potential use of these technologies for microreactors. So we do have strong work in that area to help not only develop, but to help qualify and really show a strong safety case for utilizing a heat pipe cooling technology. But we're not just limited to that. We're also looking ahead at other ways for other types of systems that may not be utilizing heat pipe technology, but maybe other more conventional systems such as gas cooling or other liquids, and seeing how that can be best optimized for microreactor applications. Similarly, we're looking at high temperature material properties and looking at various reflectors and advanced moderators, and continuing to leverage the ongoing sensor research development work. So this is more of the applications of these remote health monitoring and potential semi-autonomous control regimes that were identified and within the systems integration analysis. Now, the final area really builds upon both of those, and that's really what the focus of the scope today will be upon, is demonstration capabilities. So our program is very unique in that we are standing up two very innovative facilities to help stakeholders and end users to help validate the design, both on the component and integrated microreactor system level, both in a non-nuclear and nuclear environment. So the first system that I'll be discussing briefly is the magnet non-nuclear testbed. This is a very unique facility at the Idaho National Laboratory. It is a non-nuclear electrically heated facility, heavily instrumented, and it can be fitted with a variety of test articles to simulate a variety of stakeholders' core design or other applications that they would like to test within a non-nuclear environment. And you can really generate real-time data to simulate a variety of transients and potential coupling to power conversion systems, or simulated coupling to other process heat systems with this test bed. And there's a lot of versatility there, and it's we've done a lot of great work in our program to stand that facility up, and it's looking to be completed final construction in December with a initial test matrix beginning in the next fiscal year, and then really looking at ways to reach out to the community on how we can best utilize this facility to help them advance their technologies. And most recently, we've developed a nuclear applications testbed called the Marble Nuclear Testbed. And this is really looking to complement magnet and to provide an actual nuclear prototypical environment for essentially a two-phase approach to take on some of the higher technical risk areas, ahead of demonstration and commercial deployment, such as employing, potential autonomous operating or remote monitoring regimes, and also coupling a nuclear system to end-user applications. And, if I had hours and hours, I could go into much more detail on these, and I understand that there will probably be many questions on facilities. So what I've done is at the very end of this presentation, you'll find a link to a website that's been graciously hosted by GAIN. And that website has a variety of documents, both high level and technical detail, that describe these facilities in much more detail. One of the key points to know with Marble, it is not intended to be a demonstration in the sense it is not a commercial design, nor is it meant to compete with any commercial design. It's a very small, and we'll have some of the specs on it in a little bit. Very small, really just a nuclear generating source to build upon an overarching test bed for end user applications. But it's a very exciting opportunity and something we look to have come to fruition within the fiscal year 22 timeline. But we're looking ahead to see ways that we can potentially stand up test matrices within this facility to better end user applications. Now that we've gone through an overview of the program, I really just want to hit right on to the work scope. So the overall motivation, and this is cross-cutting throughout the majority of advanced reactor designs, is we're really looking at how would these microreactors be cost competitive. Microreactor concepts, stakeholders are identifying near-term commercialization deployment within the next decade and demonstration within the next handful of years. And to make these microreactors viable for broad deployment, they need to remain cost competitive with other available sources of energy. And to do this, we're looking at ways to really develop components and integrated systems and other applications to really make these cost competitive and really make tangible results by utilizing our experimental capabilities that we've developed within the program. So I'll basically discuss two areas. The first will be related primarily with employing the magnet application as one of the areas of this overarching scope, and then I will touch on some areas we're looking at for the marble application. So for improving economic competitiveness, very similar to advanced reactors in general, we're looking to reduce technologies and regimes that can reduce microreactor construction, operation, and maintenance costs. And those are of particular interest. And it's not limited to these, but these are some areas that may be worth considering. And that's really looking at readily deployable technologies to enable unattended and reliable operations. So not really looking at reinventing the wheel. We understand that there are other industries, other entities that utilize remote operations and autonomous regimes, and we're looking at ways of how that can be applied to specifically microreactors, and not just how it can be applied, but how can it pass regulatory muster and ways that can be implemented. So we're not looking to really develop the new technologies, just ways of implementing how that can be done in a strategic way. Similarly, looking at using embedded sensors for remote online monitoring. Another area that we've received interest from the university community is looking at ways to reduce fuel costs, really through the efficient use of fuel. A lot of designs that are have been self-identified as needing access to higher assay levels of low enriched uranium, and if there are methodologies or technologies or operating regimes that can potentially allow for the lifetimes that microreactors are looking at while using more conventional low enriched uranium that's more readily available in the near term for commercial demonstrations, that could be one innovative aspect as well to look at. Very similar, there's a variety of core structures, heat exchangers, power conversion systems that may be alternatives that are able to plug and play into these systems that very well make these more economically versatile and beneficial. And looking at ways within all of these technologies, not necessarily standing up new ways, but what are some standardizations or efficient factory manufacturing processes that can be applied to really make these factory fabricated transportable systems ready to go off the shelf to really help reduce these costs. Like I stated, we're really encouraging, really working closely with the microreactor program and laboratory point of contacts, which you'll see in that website at the end, to really leverage a variety of the experimental infrastructure we have in place, up to and including even looking at the magnet facility as well at Idaho National Laboratory. We're really looking to get them in the hands of researchers and that to really make some very high-profile and tangible results in the near term. And we're really excited for this opportunity for the universities to weigh in a variety of these areas and how that can be leveraged. And just one final thing to note is we're really looking we're looking at innovation, but we're looking for tangible outcomes that can really significantly reduce costs. So it's very important in a proposal that there's a clear description of how the proposed scope will reduce, microreactor costs, and a game plan and how these technologies regimes will be deployed and how deployed they be, and a risk assessment of how mature and what some gaps are in place. So we're looking at innovation, but we're also looking at really game-changing innovation in terms of the cost effectiveness for these reactors. The next part of the scope is we're looking at ways, really shifting beyond just the demonstration. We're looking at potential end-user applications for microreactors. And one way we look to do this is by standing up the marble facility. And this is the nuclear testing facility. And one of the major aspects of it includes the rapid development. As you can see, it's not a very large reactor. It's a 20 kilowatt electric microreactor planned for availability in FY22. And it provides a platform for improved integration of microreactors and user applications. So really, it's a viable, small enough reactor to fit within the microreactor program, where we can really reduce a lot of the technical risks that have been identified by commercial stakeholders, and take that upon the program, which is really sort of our mission to help these technological breakthroughs and reduce this technical risk in our program. But we realized very early on we need to engage with end users and with stakeholders as well. So it'll be very important to have this engagement, and this is where we really look to, university teams as well to, in a way you'll see at the bottom, to really engage with microreactor developers and end users and, develop a pathway on how this, unique application can be utilized specifically for microreactors. I really want to point out that this area is really looking at resolving very microreactor-centric end-user applications. And there are other scopes within NEAP that you may have heard about or may hear about later that are a little bit more broadly applicable to advanced reactors and integrated energy systems. And that is a good area for more broad applications and generalized topics for integrated energy systems. But this is really looking at engagement with microreactor stakeholders and really microreactor-centric end-user applications and how the MARVEL facility, test matrices that can be set up to really, utilize this to its full potential. So we're very interested in proposals as well, with close engagement with stakeholders in industry and how we can better the economic case and end-user applications of microreactors. Like I stated, this slide right here provides a website that was hosted by GAIN, and we very much appreciate that. And it provides a great overview, not just of the microreactor program, but it also provides fact sheets of Magnet and MARVEL, and also gives direct access to a variety of the technical documents that have been developed so far within our program for your viewing and research and literature search prior to your full proposal. And also provides a list of points of contact beyond just myself and Dr. Jess Gian that may be able to assist you in learning more about these capabilities and ways that universities can engage and develop a variety of technologies or operating regimes that can help improve the economic case of microreactors. So with that, I definitely appreciate your time, and I now open up for any questions you all may have. Thank you.
Hey, Tom, would you like me to unmute Jess Jehan for you?
Yes, please. That'd be great.
Questions? Yep. Okay. This is Julie Jacobson with NEUP, and I'm going to ask questions today. Jess, if you could please unmute your microphone now. There we go. Great.
Can you hear me?
Yes, we can hear you.
Great, thanks.
Okay. Yeah. If everybody would please type in any questions you might have into the question box, I'll be glad to ask them for this session. The first one is the numerical simulation of heat pipe microreactor by Moose and SAM 3D plus 2D coupling interested with this work scope? It says the work will focus on the core design to improve heat transfer coefficient and reduce fuel cost.
Right. So I'll probably have Jess jump in a little bit, but at a very high level, not to give advice on one area or another, but we've had a very in-depth work in that area currently, just in general, with applying some of these NEAMS toolkits and their optimization specifically for heat pipe microreactors. And we did have significant activities within last year's calls, very heavily weighted on optimization, integration of heat pipes. So we're not necessarily looking for a high level or really focusing too heavily on the heat pipe reactor itself in terms of its optimization. But I can open that up to Jess for further clarification on those specific activities. But that's sort of what my initial inclination is in that question. Jess, did you have anything to add to that? Or?
Yeah, I'll add to that. I agree 100%. I think to be responsive to the call language, we would want that activity to look at specific technologies that reduce cost and to be able to give some indication of how that technology would reduce the microreactor cost. So if the scope is, say, developing overall simulation models, that's probably not very responsive to what we're currently looking for. If it's modeling a specific technology option or innovative technology that can reduce costs, that would be of interest.
Okay, next question. Will proposals be considered that meet the cost reduction goals of the call but don't use MARVEL or Magnet?
Sure. So this is Tom Sawinski again. So we highly encourage the use of MARVEL or magnet, but if a proposal, can show that, they're employing other experimental capabilities to show the viability of a technology or regime that may be cost effective, that will be taken into consideration. But we're definitely opening up the door to utilize some of the facilities and infrastructure developed within our program. So I wouldn't necessarily preclude it, but it is highly encouraged to the extent possible, even if the proposal would potentially lead to subsequent work that would be directly applicable within Marble or Magnet, that would be encouraged as well. But I wouldn't say I wouldn't rule everything out that if there isn't directly within the experimental work scope, it wouldn't necessarily be ruled there's a strong enough case and explanation of an experimental regime on that.
Okay, for production cost reduction, or for production cost reduction proposals, is there an accessible database of technical specifications and designs of microreactors considered for commercial deployment?
Right, so this is Tom again. I'll have Jess weigh in a bit. So I wouldn't say that there is an open database per se of going into the exact proprietary details of microreactors. In the program, we do have a variety of technical documents out there that may give a ballpark of in terms of cross-cutting technologies for specific types, such as heat piped or gas cooled reactors that may be generally applicable. But I would sense that if a proposal is looking at addressing for specific technology, that's where we heavily encourage working with some of these stakeholders and end users, even reaching out potential microreactor companies or developers to see what they'd be willing to share from that regard. But I think most of the data that we have would either be on former reactors similar to some of the technology being considered with heat pipes, or just other generic high temperature gas reactor data that may be readily available. But I'll open that to Jess if he's aware of any other pathways for more specific technical specifications for microreactor technologies.
Yeah, thanks, Tom. Yeah, I agree with your comment. In general, there is no general database that has microreactor design information. The developer's information in many cases is proprietary, and we require partnerships with them. We do have what I would say generic designs that could form a basis of some of this work. And if there's interest, you can reach out to me and I can make connections there.
Okay, even though budgets have not been set, do you have any idea how many awards you might be hoping to give in this area?
Sure. This is Tom Sawinski again. So very similarly, with the caveat, budgets are not set, but I think when we were putting the scope together, we would usually base it off of previous years and what our expectations and funding levels were. So I would see with the caveat that nothing's been determined of that, but I would assume anywhere between 2 to 3 within this scope area is what I think would be our ideal number, which could shift one way or the other depending on final budget allotments. But I believe that was our mindset as we went into this.
Okay, next question. Are concepts other than heat pipes allowed?
Yes, absolutely. So like I said earlier, I know it seems that's very heat pipe centric, and really so far it's been heavily weighted towards that, and primarily heat pipes have been less of technically mature for applications of microreactors. And within the objectives of the R&D program, it's to really bring some of these less mature technologies to fruition, realizing that some other technologies have relatively mature bases, especially if you're looking at gas reactor or other type of liquid coolants. But if there's work that can be very specifically be related to other concepts that are microreactors and utilizing other technologies, yes, we are more than welcome. And that actually would be, I would say, a good benefit in a sense where with the amount of so much work going on at heat pipes, universities can really do a good job of notifying us of what are some of the shortcomings and other technical hurdles specific to microreactors of other technologies that are being considered by the commercial stakeholders. So yes, it's not just limited to heat pipes.
Are shielding and other deployment concerns solutions invited to apply?
Right. So it's a relatively broad scope. Those are method areas that can be invited as well. But there needs to be a clear explanation of what the benefit of the particular technology would be from a cost savings or that, and from a shielding standpoint, that could be something in terms of reduced emergency planning zones or other applications as well. I know most of the work we've really been focused on, and that I've heard from the stakeholder community, has really been focused more on reducing size through increased reflectors or advanced moderators. But if they are engaged and have a close relationship with a stakeholder that states that shielding concerns may be an issue and cost of material and things like that, then that's one possibility. Like I said, we try to keep it as broad as possible, but the key is you have to show highly recommend you show a direct correlation of how it can be a significant cost savings over what's currently being considered.
Okay, is there an interest in proposals aimed at developing artificial intelligence algorithms for autonomous monitoring and control?
That one I'll probably defer to Jess. I think at a high level, employing algorithms within the context of existing technologies, in terms of these algorithms to move or operate existing technologies or sensors or that, I think that would be viable. But in terms of standing up brand new sensors and technologies, that's not really what we're looking for in the scope area. And I mean, Jess, you can weigh in on that as well, if you'd like.
Yeah, again, it's a little similar to the response I gave earlier. If this is connected to the objectives of this call, which is related to cost reductions or applications testing, then it would be relevant. Developing algorithms and methods for autonomous operation wouldn't be as responsive to the current call. And there's likely maybe other areas in this CINR call that may be more applicable for that.
Okay, will proposals that include an industry partnership with a microreactor developer be given extra consideration?
I wouldn't state them extra consideration in a sense. I think it would be I think it'd just be a good advice, because our program is very heavily focused on helping commercial stakeholders for their near-term demonstration, and as Jess alluded to earlier, getting a lot of specific, we have at a high level and a cross-cutting level. But if I would sense if you're looking for a cost reduction or that, it would be beneficial to at least engage stakeholders and commercial entities that are interested to at least get a sense of what some of their needs are. I mean, we do have abilities, we do engage with industry, but really going down the technical details and their needs, I think it would be beneficial. I'm not going to say yes or no, would it make it wouldn't put one proposal over another. That's not really my place to say, but I would say it would be sensical, I would think, if we're given the focus of the program to bring these to fruition in a commercial sense, it seems to make sense to try to engage stakeholders to the best of their ability.
Okay, is advanced materials and manufacturing towards microreactor design an interest in this work scope?
Very similar, like Jess stated, we're not looking to step on other scopes that are in other programs that are really dedicated to standing up in a general sense some of these. But if there are components or that are fabricated from that type of methodology, that there can be a clear connection to how they will benefit directly microreactors and a strong economic case, that may be something worth considering. But in terms of developing new manufacturing techniques or items like that, I don't believe that would be as responsive to this particular call, and maybe more viable in other scopes within this particular CINR this year.
Okay, are the microreactors that are targeted to be fixed, or should they be transportable after operation?
No, that's an excellent question. So at the Department of Energy, we are really focused on fixed applications. So what that means is the anticipated is the microreactor is factory fabricated, transported, nearly fully assembled to where it will operate, and then the site where it is put at is where it will operate for its lifetime. We're not looking at some other applications that are being considered by more defense applications where you would operate it, pick it up, move it to another site, operate it. that's outside the scope of the DOE R&D program.
Will other software rather than NEAMS tools be proposed to explore deployable technologies at the system level?
Right. So quickly, I'll let Jess weigh in a bit, but I think very similar, like we've been stating, the use of software technologies to bring up a tech, to show the case of a component or a technology or an experimental matrix. I don't really see an issue as long as there's a strong case. I would recommend using some of the NEAMS tools in that for design, et cetera, but I understand that, for different components and technologies, the NEAMS tool may not be applicable if you're designing just, a single heat pipe or a single heat exchanger, items like that. So you're not precluded to only use NEAMS tools for, standard, finite element analysis of items or things like that. So, I don't know, Jess, you have anything to add to that?
Yeah, I agree with that. It's not a requirement, although NEAMS is putting effort into developing capabilities to support microreactors, and we would encourage proposals that would use those capabilities and help apply those capabilities.
Okay, 2 test facilities were mentioned in the RC-2 call. Should a proposal address 2 topics or facilities?
No, it's essentially the overall arching premise of the scope is obviously making these economically competitive, and essentially these are 2 pathways that can be considered. We want to give that versatility and open up the whole experimental infrastructure we had, but you are not obligated to use both. You can use one or the other in your call. You're not obligated to have one that reaches into either. We just want to put everything on the table and make them available to interested university collaborators.
Okay, I think this is our last question. It says, can you explain the capability of the test bed at INL? And is the involvement of INL personnel helpful?
So I will give a very brief answer because to describe the capability would take a much longer call than what we have right now. My recommendation is yes, I believe the best pathway is to contact INL, either Dr. Jess Jean directly from this call, or in that website I listed at the end. It gives a variety of point of contacts within the Microreactor program that can give you ample information on these facilities. There's documents up there already that serve as a good starting point, and it gives you direct contacts from individuals in the laboratory structures that can help guide you in terms of the expected capabilities and specific technical specifications of these facilities.
Okay, I think that's all we have today. Thank you very much, Tom and Jess.
Great.
And then we will be, thanks. And then we will be back at 5 p.m. Eastern Time for NSUF 1.2 and NEAT 1. Thanks, everybody.
Thank you.